All right, welcome back, everybody. We're going to be getting into our next section, section number 9. Actually, section 9 and 10 are kind of related to each other. We're going to start to get into some of the more advanced topics, including routing. We're also going to talk about things like Cisco Discovery Protocol, Link Layer Discovery Protocol, and those things throughout these sections here. But this section, we're going to focus primarily on the aspect of routing. If you recall, yesterday we talked about the internet layer, we talked about the transport layer, we looked at TCP and UDP, we looked at IPv4 in depth, and so routing is just another extension really of our exploration of these different layers, and routing occurs at layer 3 of the OSI model. So when you are building an enterprise network, especially if you have multiple subnets and WANs and LANs and different types of interfaces and different types of networks, obviously you're going to need a router in order to be able to facilitate that communication. So what we're going to talk about in this section here is what is the role of a router, what are the router components, what is a routing table, what types of routes will exist in our topology. We're going to talk about administrative distance. I'm even going to get into a brief discussion about the difference between, say, a distance vector routing protocol versus link state routing and what the major difference is there. We saw yesterday in one of our previous discussions kind of the timeline of how routing protocols were developed. We talked a little bit about the concept of classful versus classless routing and what the benefits are of classless routing in terms of subnetting and being able to subnet and use variable length subnet masks in our network. So really the role of a router in a network is to take data from one broadcast domain and move it forward or switch it to a different broadcast domain, ultimately trying to get that information to its final destination. Routers do this by analyzing the packet header information. Specifically, they look at the destination IP address in the packet header, and they make a forwarding decision based on that destination IP address. Unlike a switch, though, and this is really important to understand, switches flood information when they don't know where the destination is. Routers drop information when they don't know where the destination is. Routers never flood information. So there's one database inside of a router that provides us the ability to make a forwarding decision, and that is called the routing table, or more appropriately called the global routing information base, or the global RIB. When the router receives a datagram, it does analyze the frame information of that datagram. Remember, frame is layer 2. It looks at the frame information of the datagram, but only for the purpose of identifying whether or not it needs to open up that datagram and process it. Once it's determined that it needs to open up that datagram and process it, the frame no longer matters. The layer 2 information no longer matters. So let's say, for example, host A here wants to talk to host B. All right? The source MAC address of the frame from host A is going to be the MAC address of A. The destination MAC address of the frame generated by host A is going to be the router's interface. Because again, routers operate at layer 3 of the OSI model. Frames are layer 2. Switches use frames to make forwarding decisions. So the only importance of that frame is to get the data over the local LAN to the router. So the source MAC is A, the destination MAC address is going to be the router. When the router receives that data, it looks at the layer 2 header, the frame header, and it says, is the destination MAC address my interface? Assuming we're running Ethernet. Not all interfaces have MAC addresses. There are some interfaces that don't have MAC addresses. But is the destination MAC address my interface? If the destination MAC address is not my interface, I discard the frame. I simply ignore it. If the destination MAC address is my interface, I process the payload information. I don't make a forwarding decision based on the frame. I have to open up the envelope, if you will, the frame being the envelope. I discard the envelope. I throw away the frame information, right? I don't care about that frame information anymore, and I look at the destination IP address in the packet header at layer 3. I compare the destination IP address of the packet to my routing table, and I say, do I have a destination in my routing table for this packet? Okay? Now that could be a directly connected route, which it would be in this particular case, or it could be a dynamically learned route from a routing protocol or routing process, or it could be a static route, which is a route that you define as an administrator. So there are 3 fundamentally different types of routes in a router. Connected routes, which are routes of interfaces that are physically connected to the router. Dynamic routes, again, routes learned through a dynamic routing process like OSPF or EIGRP or BGP. And then finally, static routes, which are routes that you define as a network administrator. Once I've determined that there is a destination, what is the ultimate goal of the router as far as routing that data? Where am I sending that data to? There's a specific term that we use to describe that. It is called the next hop. We're sending the information to the next hop. Now, in this particular case, there really is no next hop because the destination is directly connected. But if there was another router downstream, I would be addressing or sending that packet to that next router. Routing is always about getting the packet to the next hop. That's a very, very important concept. We never really define specifically the entire path. We say, okay, it's almost like passing the baton in a relay race, right? My goal is to get this baton to the next racer. I'm not trying to get to the finish line. I'm trying to get the baton to the next racer. And I hand off that baton, and then that racer is responsible for taking that packet down the track to the next racer, and then to the next racer, and then finally to the destination, the ultimate destination, which is the final host. All right? So the router has done its process. It's looked up the destination address in the routing table. And again, we're matching network destinations. We're not matching specific hosts. This is where those network IDs that we talked about yesterday come into play. But we match the destination network. I've made a decision that I'm going to route the packet out of this interface. What do I have to do with that packet next? I have to put it back inside of another envelope. I stripped off layer 2 on the ingress interface. I need to rebuild layer 2 on the egress interface. What is the source MAC address of that frame going to be as it leaves the router? It's going to be the interface of the router. This fast Ethernet interface has a MAC address. That becomes the source MAC address of the frame. The destination MAC address would be the host. So we do a layer 2 rewrite or a layer 2 strip and replace every single time we go through a router. Every time. There's no exception to that rule. Layer 2 frame information never makes it through a router. Ever. Okay, so layer 2 is always stripped off and then always recreated on the other side. Now, it may not always be Ethernet to Ethernet. It could be Ethernet to serial, right? So maybe this side is an Ethernet link, but this side is a serial link running frame relay. Or maybe this side on the left is an Ethernet link, and this side is a serial running PPP. But layer 2 encapsulation is always going to be recreated. Okay? So in this particular case, we have 2 separate broadcast domains, LAN A and LAN B, and the router is responsible for switching data from one broadcast domain to the next. Now let's say, for example, on this router I'm running OSPF and I'm running EIGRP and I have some BGP running and I've got some static routes and I've got some connected routes. How many routing tables do I have? 1. Okay? The router's only going to have 1 routing table. The exception to that is if I'm running multiple protocol stacks. If I'm running IPv4 and I'm running IPv6, we would have a separate routing table for v4 and we would have a separate routing table for v6. But it doesn't matter how many routing protocols I'm running. It doesn't matter how many types of routes I have. I only have 1 routing table. And what goes into that routing table? The best possible path. All right, we'll get into this in more detail a little bit later on, but we determine the best path. It really depends on how the route is being learned, but we determine the best path by something called a metric. We use metrics to determine the best path. And again, EIGRP has a different way of calculating a metric than OSPF does, than ISIS does, than BGP. Each of those algorithms or each of those protocols have different algorithms for deciding the best path. All right? All right. Now, I already mentioned this, but they mention it again here. Routes that are physically connected to the router. These are called directly connected routes. So this particular router has 3 directly connected routes. This router here has 4 directly connected routes. How do directly connected routes actually end up showing up in the routing table? I go to the interface, fast Ethernet, serial, whatever the interface might be. I assign an IP address and a subnet mask to the interface, and I turn it on. That's it. Directly connected routes show up automatically in the routing table. As long as the connected interface is in an operational state, as long as it has a valid IP address and a valid mask, that route will show up in the routing table. All right? But what about from router X's perspective? Router X is sitting here on the left. It's got 3 directly connected routes, but it doesn't have any routes here. These routes are not directly connected is what I mean to say. So how does router X know that the 10 and the 20 and the 30 subnet exist? How would router X know that the 10, the 20, and the 30 subnet exist? It would have to learn about those networks. All right? And again, there's only 2 ways to learn. Through a dynamic routing process, where you might be running, say, for example, OSPF on this router and OSPF on this router, and they're sharing information back and forth with each other, or through static routing. Maybe through static routing they can learn information, right? Where you as an administrator, you come into the router and you say, hey, router X, if you want to get to the 10.10.10 subnet, send your packet to this neighbor. If you want to get to the 10.10.20 subnet, send your packet to this neighbor. See, a switch is a lot different, isn't it? Switches build their database based on information flowing through the switch. If I see MAC address X coming in on port 1, I map MAC address X to port 1. We just do that automatically. It just happens automatically. Routers don't do anything automatically. Even if router X happened to see a packet for some reason, router X happened to see a packet come in on this interface from 10.10.10.10, it's not going to automatically say, oh, well, that means the 10.10.10.10 subnet must exist on that interface. You have to explicitly tell the router how to route. All right? That's a very, very important distinction between switching and routing. Routers don't do anything automatically. They have to be told what to do. All right, and that's, of course, what we're going to be seeing hopefully later today as well as tomorrow when we get into OSPF and we start talking about configuring OSPF. All right. What are some of the router components? Obviously, Cisco has lots and lots of different router platforms. They have small routers, and they have big routers, and they have routers with kind of fixed configurations, and they have routers with modular configurations where you have these interchangeable slots. This is an example of one of those routers. This happens to be a 4000 series router. And we can see here that we've got different types of interfaces. There's a 4-port serial interface. There is a 4-port, looks like a, I don't know, let's see here. If I zoom in, I can't really tell. The image is a little bit fuzzy, but it's either fast Ethernet or gigabit Ethernet, most likely gigabit Ethernet. And then we have some SFP slots here that correspond to these gigabit Ethernet ports. So this is, 4 different gigabit Ethernet ports. They might not actually be 4 different ones. They might be, these might be the optional ports to these. So you can put in a fiber module and so on to be able to connect a fiber interface, right? But routers also have the same types of components that we saw with our switches. They have different types of memory. They have a CPU, they have a motherboard, they have RAM, dynamic memory, they have NVRAM, which is our non-volatile memory. Remember what's stored in RAM? Running config, right? Our running config is stored in RAM. This is also where all of our dynamic databases are constructed. NVRAM is where we store what? Startup config, right? The startup config is stored in NVRAM. We have our boot ROM, which is like our boot flash. And then we have our regular flash, which is basically like our hard drive for the device. That's where our iOS is stored, and other files that are necessary for that router to function are stored there as well. Okay? So the CPU is certainly the main processing unit, if you will. And that's actually one thing that I wanted to talk to you guys about, because we haven't seen it to this point yet. But there's a concept in these platforms. There's basically 3 planes of existence on these devices. And let me pull up a diagram real quick here. Let's say, yeah, this one is probably a good one. It doesn't have the management plane, but I can explain the management plane function to you guys a little bit later on. So let me pull up this image and drag it over. So devices have, and this applies to switches as well as routers. They have 3 planes of existence. They have what we call the control plane, they have the data plane, and they have a management plane. The control plane is the CPU functions. Those are the processor level functions. That's where our routing protocols operate at. That's where ARP caches are built. And all of the higher level functions are built at the control plane. Basically, the CPU processed functions. The data plane is the interface level, the hardware level, the ASICs, the forwarding data that we use at the ASICs. So we have a forwarding table at the data plane, which is built from something called Cisco Express Forwarding. We have our physical interfaces, we have our physical ASICs at the data plane. So if data arrives, say, for example, on Fast Ethernet 01, because of the caches that we have in the data plane, we might be able to switch that data directly across the data plane to another interface without having to send that data up to the control plane for processing. Ultimately, that's the goal, because that gets us close to wire speed function as opposed to control plane function or software function. But if I have OSPF packets that are being generated, like hello packets or database descriptor packets or link state advertisements or whatnot, those have to be processed at the control plane, the brains, if you will, of the device. The management plane, we don't see that listed here, but the management plane is really just the plane that we use to manage the device. So that would include things like SNMP, Telnet, SSH, the pieces of or the functionality that requires us or allows us to manage that particular device. We've talked about all these components before, right? The RAM is my working memory. It's volatile, so if I lose power, whatever's contained in the RAM goes away. NVRAM is where my startup config is stored. It's actually non-volatile. That's what the NV stands for. That stores my startup configuration. NVRAM is actually technically a partition of the flash memory. So if you were to physically remove the flash from the device, you would be removing your NVRAM. The ROM is my bootstrap code. It's used for the post, for the power on self-test, but it's also used to load the boot instructions, right? What type of iOS am I going to load? What is my configuration register for the device? Am I going to boot normally? Am I going to bypass the startup config? Am I going to bypass not the startup config, but the iOS loading and stuff like that. But it is the bootstrap, the bootloader, if you will. And then flash is my hard drive. That's also non-volatile. It's a static or solid state storage device. It could either be a DIMM that's inside on the motherboard, or it could be a compact flash card that's external to the device. But it stores our boot images, it stores other files, and so on. And then, of course, we have all of our interfaces and our ports, right? On our devices, we have physical interfaces, and those will vary depending on the type of router we have. We also have maybe some management ports. So we've got out-of-band management ports like a console port or an auxiliary port. We've got maybe an out-of-band TCP/IP management port. So for example, when you see like a service port like this or an Ethernet port that's separate from the functional ports on the back, this is used for out-of-band management over TCP/IP. And a lot of the newer devices incorporate these types of management ports because we don't want to necessarily manage our device over the same network that our data is flowing over. For security reasons, for basic management reasons, we want to keep that separate. All right, so a router itself, what are the primary functions of the router? Well, path determination is one of those primary functions, right? We can't just arbitrarily build our routing table. We have to build our routing table in a logical way. We have to be able to identify how the routing table is going to be built, and that is done based on the type of protocol that we're running, right? Maybe we're running OSPF. OSPF has a different way of interpreting paths. It has a different way of identifying the best path, and so what will happen is it will run its algorithm, which happens to be the Dijkstra's algorithm or shortest path first algorithm, and then based on that information, it will build the routing table, okay? Path determination is done, especially if we're doing like non-directly connected paths, is done based on how the path is learned, all right? And that's one of the things that we learn as we go through and talk about each of these protocols is how is the path determined based on the type of protocol that you're running, okay? And in our case, that would mean the algorithm that we're running. Notice it says here the router is called, well, let's actually go back a little bit. It says here, routers use their routing tables to determine how to forward packets. Each router maintains its own local routing table, which contains a list of destinations that are known to the router and how to reach those destinations. There's actually two variables that allow us to define how to reach a destination on a router. What is the exit interface What is the next hop? Okay? We'll get into this a little bit later on when we talk about the routing table, but oftentimes that's a recursive process. So we learned about a destination via OSPF. Okay, that means that that network is not directly connected, but that route points to a next hop. That next hop is directly associated to a connected route. So we learned about the final destination through OSPF, and that OSPF route points to a next hop, but the next hop is tied to a connected route, not the OSPF route. So there's always kind of this recursion, if you will, in the routing process. And I will show you that when we get into our discoveries later on. We're doing our OSPF discoveries. We'll talk about that, okay? So it examines the destination IP of the packet. It searches for the best match between the destination address and what's in the routing table. By the way, it is entirely possible to have more than one route in the routing table to match a destination. In that particular case, there are a specific set of tiebreakers that we use to determine which route we're going to use. We don't ever route, unless we're doing ECMP, equal cost multipath routing, we don't ever route over multiple interfaces. We route to one destination. I don't want to talk about that right now, longest match routing versus administrative distance versus metric and so on. There's lots and lots of different ways to determine which route to use. So we'll get there eventually. We'll start to progress and kind of learn that information as we go through. All right? We may match to a directly connected route, or we may match to a dynamic route or a static route that points to a directly connected route. But we always send the traffic to the next hop. Routing is always about sending the packet to the next hop, not sending the packet to the final host. Certainly we identify the path based on the final destination prefix, but it's our job is to get that packet to the next router. That's what our job is. So the packet forwarding process is the second part. Once I've determined that I can route, the next step is to actually forward the packet. And this is what they're describing in this particular case based on this diagram is that packet forwarding process, which is what I described on the previous diagram, which is where we strip off layer 2 and then we make a routing decision, and then we have to re-add layer 2 back, and then we route the packet to its destination. So here's the routing table for A. Notice there are 3 interfaces attached to this router. There are 3 interfaces attached to this router, so you would expect to see 3 directly connected routes. Make sense? We have 3 directly connected routes. Again, for those directly connected routes to actually show up, it's really simple. Configure the interface with an IP address and a mask, turn the interface on, make sure it's functional, the directly connected routes show up. That's it. But we also have this destination network here, 10.1.3.0, that is not directly connected. So that has to be learned somehow. Again, router B might be talking OSPF with router A or EIGRP, and they're exchanging that information with a dynamic protocol. Or router B or router A might have a static route that points to router B, and so on. Let me talk to you guys real quickly about this idea of route recursion. Let's say that this PC over here, this PC right here, wants to route to this PC over here. So 10.1.1.5 wants to route to 10.1.3.5. Okay? What does this computer have configured on it that allows it to even attempt to send a packet to 10.1.3.5? It has a default gateway. Default gateways allow hosts or clients or devices to send packets to their router when the destination is not in the same subnet. So this PC over here says, oh, I have a default gateway, my default gateway is 10.1.1.1. So I'm going to address my frame to 10.1.1.1, the MAC address of this router, and I'm going to send my packet to the router. The router is going to say, oh, you're trying to talk to 10.1.3.5. Do I have a route in the routing table for 10.1.3? Yes, I do. We don't know how this route was learned. Let's just assume it was OSPF. I've got an OSPF route in my routing table that says, if you want to get to 10.1.3, you need to send the packet to 10.1.2.2, which is a next hop. Guess what type of route 10.1.2.2 is always going to be associated with? A connected route. The 10.1.2.0 subnet is connected. This is the recursion that I was talking about. I use the dynamic route to identify the final destination, and then I use the connected route to identify how to get to the next hop. So this would be my exit interface. This is the next hop. So I build my datagram and I send it to router B. Guess what happens? The source MAC address of the frame is router A. The destination MAC of the frame is router B. Because layer 2 only matters in the subnet. Layer 2 only matters in the broadcast domain. The source IP address of the packet is host A, the original source. The destination IP address of the packet is host B. So when this router receives the packet, it does exactly the same thing. It says, oh, well, first it says, is it for me? Because it looks at the frame. But when it makes its routing decision, it says, do I have a route to the 10.1.3 network? In the case of router B, that is a connected route. See what I'm saying? You were asking about this yesterday. You're saying, I can't reach the my IP helper's not working. This is how you have to analyze routing. You have to analyze routing hop by hop by hop. Does this router know how to reach the next hop? Does this router know how to reach the next hop? Does this router know how to reach the remote destination? But not only do you have to do it in one direction, you have to do it in the other direction as well. Just because router A has a route to the 3 subnet does not mean router B automatically has a route to the 1 subnet. See what I'm saying? If I put a static route in router A that says to get to the 3 subnet, send it to B. Great. But what if I don't put a static route in router B that says to get to the 1 subnet, send it to A? Then I can route to the destination, but I can't route back. You see what I'm saying? Now, when you're running dynamic routing protocols like EIGRP and OSPF, usually the exchange of information is in both directions. But it does depend on a couple of different things. Maybe I didn't put a network statement for this network or something like that. We'll get into that when we get into the routing protocols a little bit later on. So a routing table is basically everything that I know. And like I said, there's 3 things that you can basically know. You can know what your directly connected routes are, which are the ones that are physically connected to the router. You can know what you learn from other routers through a dynamic routing process, or you can learn via static routes. Now it says static and default. We'll talk about the difference between static and default later on. But a default route is technically a static route. It's just a different type of static route. So these are really kind of the same. The default and static, they're kind of the same. But these are routes that you define as an administrator. So like I said, a directly connected route are the routes that are physically attached to the router. So you go into the router, you configure an IP address, you put a valid IP address on the interface, you make sure that the interface is turned on. The interface still has to be active, right? You still have to have a cable plugged into it. Basically what I say is the interface has to be up. Remember we talked about that? Up, physical layer, up, data link layer. Show IP interface brief shows us that. Or show interface shows us that. The interface has to be up, up. All right? If the interface is up, up, and it has a valid IP, it will go into the routing table as a connected route. And that's what we see here in the routing table. Now, connected routes are kind of interesting. This wasn't the way it used to always be, but in the newer versions of code, Cisco does this now. Traditionally, the only route that you would see in a connected scenario would be the route with a C next to it, right? This is what we refer to as the connected route. A route with a C next to it. The C is the code. That indicates how the route was learned. All right? Notice that it identifies the destination network, not the destination host, but the destination network. This is what we talked about yesterday. We were talking about subnetting. We talked about the network ID. This is literally the network ID. All right? It is directly connected, and here is the exit interface. Now, what Cisco does now is they also add something called the local route. The local route represents the address on the interface. You will never see a local route without a connected route. Local routes are directly associated to connected routes. We don't use local routes for routing, but the local route is there to identify the address of the interface to basically identify how the router is participating in the subnet. All right? So the C indicates how the route was learned. It was a connected route. If it was OSPF, maybe it's an O. If it's BGP, maybe it's a B. If it's a static route, an S. If it's EIGRP, it would be a D, because E was already taken by EGP. All right, so it's the routing table is a very simple kind of thing that we analyze, and again, it's pretty common across most platforms, even across vendors. The routing tables are kind of built the same way. The other option we have is to learn routes via dynamic routing. And we've been doing routing for decades, right? I mean, the first routing protocol came out in the mid-'80s. EGP was 1983, I think, the very first routing protocol. So it's been around for a while. But even to this day, we really only have a handful of routing protocols. There are basically 5 major routing protocols: OSPF, EIGRP, ISIS, BGP, and RIP. I'd say RIP last because RIP is kind of a useless routing protocol. All right? Now, that doesn't mean there aren't other ways to learn routes and there aren't other routing protocols, but these are predominantly the most common routing protocols. In fact, the 2 most common routing protocols are OSPF and BGP. Not that EIGRP isn't a good routing protocol. It is a good routing protocol, but up until only recently, it was proprietary to Cisco. So OSPF became kind of more of a popular routing protocol because it was open standard. IETF. It's an IETF routing protocol. All right. Now, these routing protocols themselves are vastly different. Vastly different. Routing protocols like OSPF and EIGRP, they have some similarities. Maybe similar data structures like neighbor tables and topology tables and so on. They have similar message types like hello packets and updates and replies and queries and so on. But they are completely different protocols. A dynamic routing protocol allows me to learn about destinations automatically. So it's like if all of us are routers in this network and we all want to exchange our information, we can agree to use a single language to do that. Could be EIGRP, could be OSPF, whatever. Okay? If you're really interested in learning more of the advanced stuff about these routing protocols, because we only really talk about basic OSPF in this class, go to the YouTube channel, check out the ENARSI course. That's the advanced routing course. And there are several videos out there about advanced EIGRP, advanced OSPF, basically the same types of recordings that we're doing for this class, but for those advanced routing protocols. And by the way, all those, the labs, the demonstrations that you see in those videos are built in GNS3 using the same platforms that we're using in this class. So you could actually probably kind of build your own platforms and start practicing those topologies as well. All right, there's a lot to talk about when it comes to dynamic routing protocols. When I teach my CCIE class, for example, I'll spend 20 hours talking about OSPF or 20 hours talking about EIGRP. So we're just scratching the surface in this class about what these protocols do, how we configure them, how we manage them, and so on. I'll try to give you as much information as possible. Obviously, we have a lot of information to cover here, so this is really just basically an introduction, if you will, to these protocols. All right, but like I said, the routing information protocols, we identify the route source. So for example, how was the route learned? Maybe it was learned through OSPF. That's a 0, but it should be an O. Maybe it was learned through OSPF, so you would have an O next to the route. And even in OSPF, there's different types of routes. There's OIA, there's OE1, OE2, ON1, ON2, O, and so on. So there's different ways to learn routes even within the protocol itself. We have a destination network. That destination network, let me just go to the diagram here and kind of describe what we're seeing in the diagram. You have the destination network, right? And that destination network allows me to identify the destination prefix that I'm trying to reach. So here's that code that indicates how the route was learned. Here's the destination network, which is my overall destination. I'm going to skip over the middle part real quick. This is the next hop, which is going to be tied to some sort of connected route. This is how long the route has been in the database or how long it's been in the database without being updated or changed. And then this is the exit interface that I go out of to reach that destination. But what's in the brackets here? That's kind of important actually when it comes to routing. What's in the brackets defines two things. The first thing is something called administrative distance, which we'll talk about a little bit later on in this section here. The second thing is called a metric. That value is called a metric. Every routing protocol has a different way of defining metrics. Metrics are the way that we define how a route is actually measured as far as efficiency, as far as reaching that destination. Let me explain a couple of things here because this is a really, really fundamental concept to understanding routing. All right? Let's say that I have a router here, all right, and I am trying to reach a destination. And that destination is 3 hops away. Here's router 1. And I'm running OSPF, and all 3 of these routers are running OSPF. So this router is advertising network X to its peer. That router is then advertising network X to its peer. And this router decides to get to network X, send the packet there. This router says to get to network X, send the packet there. To get to network X, use my connected route. So far, so good? So this is an OSPF route. This is an OSPF route, and that's a connected route. And then, of course, I would have to have a path going back to reach maybe a destination going back as well. We measure the efficiency of reaching that destination based on a metric. Based on a metric. We don't have to get into the specifics of how metrics are calculated in an OSPF. It's an inverse proportion of the bandwidth, 10 to the power of 8 divided by the link bandwidth in bits per second. In EIGRP, we use a composite metric that has 5 K values, bandwidth, delay, reliability, and load. And then we put it into a formula. But every routing protocol has a way of evaluating paths to determine the best path. So let's say in this particular case, I added another path to this destination. So we have another router here, and maybe we have alternate path to reach that destination. So now this router here is not only advertising X down this way, but it's advertising X that way. And this router now needs to make a decision. Do I use the top path or do I use the bottom path? Now keep in mind, we're learning about this route through the same routing process, the same routing protocol. So the tiebreaker, the decision that we use to choose the top path or the bottom path is the metric. And the path with the lowest metric is the path that goes into the routing table. If this path costs less than this path, then we use this as our path, and that goes into the routing table. All right? I'm going to leave this diagram because there's actually some other deciding factors if there's more than one way to learn about a route. What if those paths happen to be equal? What if they had the same metric? If they had the same metric, we would do something called ECMP, equal cost multipath routing. I would basically route over both paths if they have the exact same metric. So that value that you see in the database, this value here was the value used to determine the efficiency of this path. That is the metric. And most likely, it's the lowest value of all the possible paths that I have. Administrative distance only comes into play. Now, I don't know that I want to, we are going to see administrative distance in this section here, but if I'm only running a single routing protocol, that number is never used to determine which path. Never. All right? So we've talked about one of the tiebreakers. One of the tiebreakers, or one of the deciding factors in routing, is what is the best path based on metric. All right? A static route is where you basically go in and you define the route manually. You say, okay, to get to this destination, to get to the 30 subnet, you need to send your packet to this address. Notice there is no metric for a static route because I'm not evaluating a path. I'm literally telling you manually what path you should choose. I'm not evaluating a path. Okay? I'm not evaluating a path based on dynamic variables, right, like a metric. The problem with static routes is that they don't change. Right? If you define a route and you say go to this destination, then the router is going to always go to that destination. There's only two reasons why a static route would not show up in the routing table. If the connected network that's tied to this next hop goes down, then the static route goes away. If the interface, right? There's an interface tied to that 10 subnet. If that interface goes down, the router's smart enough to say, well, the interface is not there. So I'm obviously not going to be able to route to that destination. So we take the static route out. All right? So a static route allows you the ability to define a route, and there are instances where static routes are better. In this particular topology, static routes would not be good, right? Because if I have a static route pointing to this interface, and that link goes down, then my routing stops working. Now I could do floating static routes and use this as an alternate, but again, if I define a static route here, then I have to define a static route here, I have to define a static route here, and then I have to do static route here, static route here, static route here, static route here. So it's not very scalable, right? Defining static routes are not very scalable. That's why we like to use dynamic routing protocols. But if we have a stub network, static routes work very well. A stub network is basically a network where you only have one way in and one way out. Right? And in that case, static routes work very well because there's only one way to go. right? It could be maybe a default static route, or it could be a qualified static route, you know, that includes next hop and exit interface and all that. All right? So administrative distance is something that we haven't talked about yet, and we will, I promise. It's in this section here. But so far it hasn't come into play because we don't have multiple information sources. But certainly we know when we're looking at the static route, we're talking about next hop, we're talking about the destination prefix. This is the prefix. This is the prefix length. Subnet mask. Okay? So this is a 24-bit mask, which means the network ID is 192.168.30. Okay? We'll again talk about some of the tiebreakers. A default route is the only time that a router will never drop a packet. Because default routes, we call these the gateway of last resort, because a default route is kind of like, okay, if I don't have any other way to route, I'm going to go ahead and use the default route. Typically, default routes point towards the internet, right? Because we have potentially hundreds of thousands or even millions of destinations on the internet, and I don't want to have a route for each one, so I use a default route to be able to route to the internet. The default route has a very specific format. Any network, any mask. This is the least specific route that you can have in your routing table, because the prefix length is 0 bits, which means we're not really technically matching on any bits, which means anything matches. All right? Default routes can be programmed, but usually it's called the gateway of last resort because if I'm matching a packet against my routing table, and for some reason that packet doesn't match any of the other routes in the routing table, but I have a default route configured, then the packet will use that default route. All right? This is a route that you have to specify as an administrator. It is a static route. It is a static route, so it looks just like a static route. It has an administrative distance of 1, and it doesn't have a metric because we're not actually learning about a path dynamically. But it is the gateway of last resort. So take a look at this routing table here, and let's kind of zoom in a little bit to make it a little bit easier to see. Let's look at what's in this particular routing table. First of all, we look at the routing table by using the command show IP route. Now, it would be slightly different if we were running VRFs, right? If we're running a virtual routing instance, we would do maybe a show IP route blue or show IP route green or whatever based on the VRF name. And we would also have a different command for IPv6 if we wanted to see an IPv6 route. But these are all the ways that we can learn routes in a Cisco router. Local routes, connected routes, static route, RIP route, BGP, EIGRP, OSPF, there's several different OSPF, ISIS, on-demand routing, basically all the routes that we talked about primarily. The gateway of last resort is set, so this particular router has a default route. You can always see the default route because it's the route that has the asterisk next to it. It doesn't necessarily have to be static, by the way. You can actually learn default routes through dynamic routing protocols as well. OSPF has something called default information originate that allows me to inject the default route into an OSPF domain. So a default route doesn't always have to be static. All right? We've got a connected route and, of course, the associated local route. We've got a RIP route. We've got an OSPF route. We've got a EIGRP route. And we've got a couple of static routes and then another connected route. All right? Each of these destination prefixes are unique. 172.16/16, 172.16.1, 192.168.20, 192.168.30, 192.168.10. But let's talk about the second tiebreaker. This is really, really, really important. we have overlapping routes. 172.16.00/16 and 172.16.1.0/24. Isn't 1.0 included in 172.16.00/16? So what happens if I send a packet to 172.16.1.1? Am I supposed to match the RIP route, or am I supposed to match the OSPF route? I'm going to match the OSPF route. Why? Because it's the longest match. That is the next tiebreaker that we talk about. Routers always do longest match routing. It doesn't matter that it's OSPF or RIP. It could be the other way around. The longer match could be RIP and the shorter match could be OSPF. It doesn't matter. Longest match routing is always used because technically every single packet also matches that route. So there's technically 3 routes that match the 172.16.1.1 packet. But this is the shortest match. So that's the last route I would ever use. That's why it's called the gateway of last resort. All right? So longest match routing always is going to be a deciding factor. Of course, for the EIGRP route and this static route and this connected route, it doesn't really matter, even though they're kind of in similar address space, right? 192.168, they're uniquely different prefixes. One is a 20, one is a 30, one is a 40. And actually, this routing table is not complete. They only showed you the actual routes, but you would also, and I'll show you guys this later, you would also see entries in this database that don't have a code next to them, because the routing table is actually organized by prefixes. All right? In fact, it's always organized in numerical order, with the exception of the default route. So 10 is before 172 and 172 is before 192. We do not process the routing table top down though. We're not trying to say, okay, check this route first, check this route second. We match the destination packet against the prefix.
Would you say that it being in numerical order is more so for like user benefit?
Yeah, it kind of makes it easier to parse the table, and it has nothing to do with the order of operations though. It has nothing to do with how the routes are processed. All right. So we talked about the C as a connected route, the L is a local route, R is a RIP route in this case. RIP is just another dynamic routing protocol. It's a very, very bad dynamic routing protocol, but it is another dynamic routing protocol. O for OSPF, D for EIGRP. The D is actually, E was taken by EGP. Remember, EGP was the very, very first routing protocol that was invented. It doesn't exist anymore, but for some reason they still have a code for it, right? You can see the code. Actually, is it even in here? Nope. So they've removed it because it's a deprecated protocol, but they didn't rewrite EIGRP to use it. You do see E1 and E2 for external OSPF, but those would have an O next to them. OE1, OE2, ON1, ON2, OIA, these are inter-area, these are, we get into that, maybe. We certainly do in the CCNP enterprise class, but all right. So, and then the S is a static route. Asterisk just indicates that it's a static route. It doesn't necessarily mean that it is a default route, right? S doesn't, always mean a default route. The asterisk always means a default route, or a default candidate at least. All right? So path determination, as we mentioned before, the way that we determine the best path, what is the best path to the destination network, is the metric. Now, metric is a term that we use generically to describe the evaluation of a particular path. All right, so for this, in this particular example, if bandwidth is part of that consideration, which it is primarily for most modern routing protocols, EIGRP, a major component of the metric is bandwidth. In OSPF, the only component of the metric is bandwidth. So would I take the path going this way from router 1 to router 2, or would I take the path going to router 3? This path is a gig, this path is 100 meg, so most likely I would choose the path to router 2. Different routing protocols have different ways of evaluating paths. RIP uses hop count. So actually, from RIP's perspective, RIP would use this path because it is 1 hop, 2 hops to go that way. It's 1 hop, 2 hops, 3 hops to go that way. That's one of the reasons why RIP is such a horrible routing protocol. It uses hop count as a metric, not bandwidth, or not something in relation to the efficiency of the link. It doesn't care what the link is. This could be a 1 kilobit link, and this could be a 10 terabit link, and RIP would still choose the 1 kilobit link because it's the fewer hops. Yes, sir?
You mentioned earlier, a few days ago, that you can change the bandwidth on an interface.
Yes.
OSPF and the ERGRP use that advertised bandwidth or the actual bandwidth of like...
Configured bandwidth. So yes, you can change the bandwidth of an interface. It doesn't actually change the bandwidth. It doesn't change the physical throughput of the interface, but it changes how algorithms look at the interface. And it doesn't matter. It could be a T1, and the maximum practical throughput of a T1 is 1.544 megs, but you could set the bandwidth of a T1 to 100 megs, right? It doesn't change it to 100 meg. It just changes how processes evaluate that path. And it's not just routing protocols, right? It could be QoS. If you have some sort of QoS policy that is measuring or determining path based on bandwidth. So there's a lot of ways to influence path selection. We call that traffic engineering or routing based on policy or whatever. But yes, we're not measuring the actual throughput. We're measuring bandwidth based on a theoretical value, a theoretical value, the configured value, or the default value for a particular interface, right? Fast Ethernet, 100 meg per second, gigabit interface, 1 gig per second, and so on. All right? But yes, that is a way, by the way, of influencing path selection by changing the bandwidth. Of course, RIP doesn't do that because RIP uses hop count as a metric, so it doesn't make a very good decision, right? EIGRP, OSPF, they use bandwidth as part of their metric. EIGRP also uses delay by default, which is another fixed value based on the interface type that you can modify. BGP is an interesting protocol because BGP doesn't use metrics. BGP uses something called path attributes. But BGP is not a protocol that you run inside your network. It's not an interior routing protocol. It's an exterior routing protocol. It's what we use to route across the internet. So it is a completely different monster, if you will. It doesn't operate like your traditional routing protocols. All right? So let's talk about the third tiebreaker. The third tiebreaker is something called administrative distance. Let's go back to our diagram here, and let's say in this particular topology, let me clean this up a little bit. Let's say in this particular topology, I have multiple paths, but I'm also learning about routes through different routing protocols. All right, so trying to clean this up. Do this one here. All right. So let's say in this particular topology, I'm running both OSPF and OSPF and RIP. Okay, that's a good ones to look at. So OSPF is my red protocol, OSPF, and I'm running RIP. And there are some instances where you might do this if you're migrating from one routing protocol to the next, or if you've merged your organization with another organization and you're in the process of kind of migrating or whatever. It is possible. You can actually run 3 or 4 different routing protocols if you want to. There's really no reason to. There's no reason to run multiple routing protocols, but there are special cases where that might happen. We're talking about administrative distance in this particular case. RIP, let's say that this link is 100 meg, this link is 100 meg, this link is a gig, this link is a gig, and this link is a gig. All right? OSPF is going to choose this path because one of the major components, or pretty much the only component of the OSPF metric, is bandwidth. Right? So the faster the link, the lower the cost. The lower the cost, the better the metric, so we choose that path. So router 1 is going to have an OSPF route that chooses that path. RIP is going to choose this path. Why? Actually, RIP would load balance. Let me change it. Let me change it. I'm going to put a router here. I didn't count correctly. There's a router there. Okay. So obviously RIP is going to choose the top path, fewer hops, right? It's basically 2 hops to reach the destination. The bottom path is 3 hops to reach the destination. So we have a RIP route in the table. The metric for RIP is hop count. The metric for OSPF is cost based on bandwidth. There's no way to compare those metrics. So we have to make a decision. We can't do both. We have to choose a route. Now we know, obviously, logically, which one would be the better one to choose, right? OSPF. It's making a better decision. The way that we define which protocol we use is a value called administrative distance. Administrative distance defines the trustworthiness of a protocol, or the trustworthiness of information sources. All right? So for example, I'll just write some down. There's some in the book, but I'll write them down. A connected route, 0. Static route, 1. Let me clean this up a little bit so I have more space to write these. All right? Connected route, 0. Static route, 1. eBGP, 20. That's supposed to be a P. All right. EIGRP, 90. OSPF, 110. ISIS, 115. RIP, 120. What do you think is better? Higher or lower? Lower. Connected routes are the most trusted routes because they're physically attached to the router. Static routes are trusted because you're the administrator. You're telling the router how to route. The router better listen to you because you know what's best, maybe. So in the case of RIP versus OSPF, RIP has an administrative distance of 120. OSPF has an administrative distance of 110. The OSPF route would be used, and the RIP route would be ignored. Keep in mind, the only time that administrative distance comes into play, the only time administrative distance comes into play is if we're learning about the exact same route from 2 different information sources. All right? It is not used as a tiebreaker if the routes are different. Administrative distance is a value that we use when we have the exact same route from 2 different information sources. I just decided to pull up the whole table for you. This is Cisco, by the way. Other vendors might have a different way of defining their administrative distance values. Connected route 0, static route 1, EIGRP summary. We'll probably not talk about that in this class. Not really that relevant because it's only locally significant to the router. External BGP 20, internal EIGRP 90, IGRP, which doesn't exist anymore, that's why I didn't write it down, 100, OSPF 110, ISIS 115, RIP 120, external EIGRP, which are redistributed routes into EIGRP, that's 170. Internal BGP 200, unknown 255. And there's a couple more actually. They're not, this isn't the entire list, but these are pretty much most of the protocols. It makes sense that I'm going to trust connected routes over anything else. It certainly makes sense that I'm going to trust OSPF and EIGRP over RIP. There's kind of an argument of whether or not you should trust EIGRP over OSPF, but these are Cisco's values, so of course they're going to trust EIGRP over OSPF because they wrote EIGRP. And EIGRP is not a bad routing protocol. It's distance vector, we'll talk about that, but it's not a bad routing protocol. All right, ISIS, intermediate system to intermediate system, is a routing protocol that's still used today. It's a very old routing protocol. It's actually a layer 2 protocol, believe it or not. That's another interesting thing about these protocols. EIGRP and OSPF, we talk about routing. Routing is layer 3. EIGRP and OSPF are layer 3 protocols. They run directly on top of IP, protocol 88 and protocol 89. ISIS is actually layer 2. It exchanges routing information, but it does it at layer 2. RIP and BGP are applications. They're not even really technically routing protocols. They run at the application layer. RIP runs over UDP and BGP runs over TCP. So they're actually technically layer 7 protocols, but they do allow us to exchange what we call network layer reachability information. Okay? We'll get into some of this in more detail a little bit later on. They kind of give you just some of the AD values. In this class, this is pretty much what you deal with. We don't do EIGRP anymore in CCNA, which is a bit of a shock, honestly, but we do some OSPF and so on. All right? So we've talked about 3 different tiebreakers, haven't we? Let me pull up a notepad here and talk about these tiebreakers. If my routing table looks like this, 10.10.0.0/16 and 10.10.1.0/24 and 0.0.0.0/0, we know what the tiebreaker is here. Longest match, right? If I had 10.10.1.0/24 and I had 10.10.1.0/25, what's the tiebreaker here? Longest match. My point is that administrative distance does not come into play here. The only time administrative distance comes into play is if the routes are identical. They would have to be exactly the same. And in this case, the OSPF route would be chosen. The RIP route would actually not even go in the routing table, because we only put in the routing table the routes that we're actually using. There are other databases that are built to house routing information for routes that we're not using. They're called topology databases, or in the case of OSPF, a link state database. All right? All right. So the routing table always points to the next hop. In this particular case, we're saying, okay, we're learning about the 8.0 network from EIGRP. We're learning about the 8.0 network from OSPF. Those are going to go into the routing information bases for those respective protocols, what we call the topology table. But the route that ends up going into the routing table is the EIGRP route, because it has a lower administrative distance. You can actually modify that, by the way. You can modify the administrative distance of routes individually, or you can modify the administrative distance of a protocol. Again, it's more of a concept where you're trying to do some sort of like traffic engineering, or you're trying to kind of override how the router normally routes. In our advanced routing class, we talk about policy-based routing as well. And policy-based routing provides me the ability to override just how the router routes altogether by creating some sort of route map and defining how the router is supposed to route. All right, so this whole discussion right here is all about those tiebreakers that we've talked about. The decision the decision tree that we make, packet flow. All right, the best route from the routing process. We install the route, and if we're learning about two different routes from different routing processes, the winner is going to be based on administrative distance. Again, administrative distance never comes into play if there's not a tie, if there's not two exact routes that are the same. So it's not considered a metric. It's not really considered a way of determining the best path. It's really determining the trustworthiness of the routing protocol. And then we route based on longest match. What if it's the same destination, same prefix length within the same routing protocol? What's the determining factor there? We've already talked about it, but same destination, same routing protocol, same prefix length. Metric, right. All right, then we forward the packet. Okay? And again, various routing processes have different ways of determining the best route. The routing table itself accepts information from the routing processes and replies to requests for information from the forwarding process, meaning the routing table is what we analyze to be able to identify how we're going to reach a particular destination. All right? So that is it for kind of our introduction to routing. In our next section, we're going to get into configuring a router. We actually have a couple of discoveries that we're going to do as well. So we'll see you guys there.